Okay, so these are two references. First one for yesterday, the second one for today. I needed to make up something for tomorrow. Okay, so yesterday basically I gave a definition of everything. I trying to give you the good reason why we need to have a Zagier formula. Today, we want to answer the question, why is it true? Why is it right? Yeah, so tomorrow I will talk about what else should be right. So to answer the question, why is it right, we needed to put all the different Zagier formula, different levels, into a bigger package, so that it has some group action and that. So I will talk about instead of working on one modular curve, I will work on a towards a modular curve. So recall that we have we have E defined over Q. So this is the elliptic curve. So the gamma, the congruent subgroup S2 of Z. So in fact, probably is more, if you think about a group action, probably it's better to consider it congruent subgroup in SL2 of Q, because this way, when you consider tower, there's two something, no difference. But a group action for second one will be easier to understand. So you have X gamma will be the upper plane with the cusp modular gamma. Then yesterday I said that for certain gamma, the homomorphism of I write 0 here of X gamma of E is non-zero. So this is a big theorem. It's a combination of a theorem of Fulton's and a theorem of Weyer's, Taylor, and others. So now I want to concede the projective limit of gamma X gamma. Right? This certainly is not an algebraic variety. It's still algebraic variety because all the adjunction map is a finite map, so you still can define a certain way. If you only consider C points, this actually has a very simple description. It's the projective limit of U. So I use the same idyllic description as Kelvin's lecture yesterday. U it will be open compact subgroup of 02 of Q hat. Right. So this has action by of this GL2 of Q. Take an upper plane plus or minus. Take the GL2 of Q hat mod U. In fact, in this case, probably much simple. It's simply H plus times, modular GL2 of Q times GL2 of Q hat as a set. Okay, so this is not a canonical equal to X plus, just X plus is X self times Z hat. So it's a very simple description. So this has action by GL2 Q hat, and this description is very easy to describe. So then instead of consider this n, we can see it formally the homomorphism from this X, the given name called is X.
I'm slightly puzzled by this because you've got a limit of things which are obviously connected being something that's obviously not connected.
What?
I mean, the thing on this board has lots of components, and the thing over
Oh, I'm sorry. Oh, yeah. This one can see it as, when I wrote yesterday, this one, let me try to write that down. The x gamma can see it as a curve of a q gamma. Then you further consider as, so I can see this curve as a q curve in a two-step. First of all, this curve is a connected curve over q gamma. Then you just view it as a scheme of q. So it depends on what I mean, the C points. Depends what this notion means. This notion means I define this one as a q. Okay, so I can see x gamma as a q curve. Now you talk about C points. So in other words, when I define the C points, I already make the various different embedding to C. You need to choose the embedding to C in order to define the C points. Is that okay? Of course, I mean, this description already have a problem inside. So conjugation of Schumacher varieties is still Schumacher variety, right? So this I didn't describe. But for modular interpretation, that's a pretty normal thing. So I can see this morphism of E, and somehow I tensor Q here. I give a name called a pi E, or just a pi. So this is a direct limit of the homomorphism of x gamma E tensor Q. So this pi E has a representation, has action. By GR2 of Q hat. I didn't define the Q hat. Q hat is a completion of a Z hat tensor Z of a Q, right? The Z hat is a product of ZP. The mod NZ. So you can consider pi E is a representation of GR2 Q hat. So in fact, this representation is irreducible. Is irreducible. And sometimes it's called admissible representation, algebraic admissible. Of GR2 of Q hat. That is usually we call that the finite part of Lagrange correspondence of Galois representation. But in this way, you define the representation in one step. You don't need to move to modular form. And not only that, you get a representation with a coefficient Q. So this pi E can be decomposed as a local representation P. This is pi P, a irreducible representation of GR2 of QP. Okay, so this is one step. Okay, so I forget to say what is action here is. Action means if you have, well, first of all, I needed to specify that this thing has action from right-hand side, because this one acts on left-hand side. This action is from right-hand side. So the induced representation and the morphism will be from left-hand side representation. So let me write the action will be if F is inside pi and G inside GR2 of Q hat. G gf of x. It really means f of gx, x of g, right? Or write g here. There's a right action inside. Okay, so this is a, so I defined this representation. The second thing, as I said, I needed to, the k be q squared of d is the imaginary quadratic field. Then I want to fix the embedding. From k to, in fact, this is sufficient, 2 by 2 of q hat. Right. So this will induce an action by k cross inside of GL2 q hat. And somehow, and of course, I mean, this embedding will be embedding this one. And the k cross go this one. Then I can set this x of k cross. So this is the subscheme of points fixed by k cross. But right now it's pretty abstract. Later on I'll give you something very concrete. So, but this one will have action by, this will have action by normalizer of k cross inside is GL2 of q hat. And this normalizer is, in fact, is a group joined with generated by times j. J is some elements there to normalize k. So jx equals x bar of j. So this is the scheme of a Q with the group action. The complex theory will tell you that this also has a good action by a Galois group. Q bar of Q, right? So that's like it's a zero-dimensional scheme. Has a, as Kevin said, has a two symmetry, Heck symmetry and a Galois symmetry. But in fact, both of them make this one to be a principal homogeneous space. Both of them make them the transitive, commutative action. The same theory says that this action is given by the reciprocity law. So action is given by the Galois of KAB over Q is isomorphic to this normalizer. Over K cross. Okay? So, and these kind of points, we can interchange the action, Heck action and the Galois action. So I give you some example. There. Example, for example, you can, if K equals Q, let me write some square root of D, then you can embed this one to be 2 by 2 matrix of Q. For example, A plus B squared of D goes to A, B, BD, right? So that's like, you can make this embedding. Then you can find out the K K cross X upper plane has a fixed point. The fixed point is very easy to calculate. It's just AZ plus B dz plus A equals Z, right? So that's the point you want to find. You're trying to solve this equation. You find actually Z equals 1 over square root of D is in fact the standard, the fixed point. Right. This is actually the point used by Hingen, rather than the point used by Birch and Gross-Zagier. The Gross-Zagier used the modular interpretation. Hingen, he didn't use the modular interpretation, just take these points, calculate the value using modular functions. Then he gets the solution of dipole equation. So this is in the upper plane. Or maybe I have the negative, depends. Yeah, negative this one, right? Because yeah, because D is negative. If you put 1 over square root of D, you got the imaginary part will be negative. Okay, so far what have we done? Combine these both construction together. So if we fix, so if I fix a P here, so you get this point there. So then this upper plane goes to X of gamma, which is Z here. I get a point Z gamma, or P gamma, whatever, P gamma. And then if you take the project limit, this will get about a P of P gamma there. This will be inside X. Using these points, we can define an embedding from a torus to the Shimura curve. So we define this is the torus inside X, right? By take a T goes to, well, P to the sigma of T. Okay? The sigma, if I use this thing, maybe this map, this is what we call the sigma, for example. So this is the Shimura curve. This is the Shimura points, right? Zero-dimensional Shimura points. It is it is essentially spec QAB, right? No, okay. KAB. Inside. Okay, so now I reinterpret the Peirce integral. Recall that we defined the Peirce integral the following. So if give a P there, given F inside is a pi, right? And then we can define, yesterday we defined is a Peirce integral. I'm sorry, the chi is a character. To C cross is finite character, right? Then we define this one, chi, as the integration is there right on the Galois KB of F P sigma chi sigma dt d sigma Then using this reciprocity law, we can rewrite this one in a more fancy way. The integration of k cross h of k cross f of t chi of t dt. Right. So that's like a more familiar Peirce integral in automorphic form theory. So you see, if you think about it, I mean, there's a pi. Let me write the one big remark. I will come back to these points later. So one should review. The pi should be reviewed. The remark. Should be considered as the space automorphic forms on GR2 of QH with values in E. Right. So it's not the complex valued automorphic form is elliptic curve valued automorphic forms. Right. So that's the way you have to think about it. So this Peirce integral is not a complex number. It's in E KAB tensor C. Okay. So that's the way you should think about it. This is very important because later on we will redo the theory by replacing E by a complex number. That's supposed to have a simpler theory, right? So, but that theory was known. That's something called the Vaz-Puget formula, right? So this theory basically they redo the Vaz-Puget formula by replacing complex numbers by elliptic curves. Okay, so there's two, to continue, there's two observations which give you, which is a very key thing, key observations for the Zagier formula. So one observation is that, well, you see, if I fix a chi, I mean, this one is a functional, right? F is a functional. So F goes to P, F chi, so it's a functional, it's a linear functional. In the space, home of pi, tensor chi is one-dimensional, it doesn't really matter, but I'll put it there. I have a good reason to put it there. With the valued in E, right, of KAB, tensor C, right? But in fact, I can take this second one away, just over C, then tensor E of KAB. Right? And this linear functional, the way to write on it is the integration of the k cross of k. So in other words, the linear functional is trivial when you restrict on this group. Right? So this is a representation. This is a representation of GR2 of QH. This is a representation of k cross. Right? So I have a diagonal action. Understand? So I run a k head cross. Right? So this is a linear functional. If you let f change. Yeah, you define the integration. F is there, right? This integration there. Integrate means to take an average. Right? What? F is the choice infinite dimensional space. Modularity says at least 1. Then you can use Zagier to Q hat to take many. Once you have 1, then you have many, right? Yeah, so it means that irreducible representation of Zagier to Q hat. Is that exactly? Yeah, I mean, okay. So probably you want to think about what's the connection with the new forms, right? New form means that you don't really new forms means that this representation you take certain invariants gamma not of n, right? In my case, it's called u not of n, same thing. This dimension is 1. Right. So that's the generator of this form is the new form we usually talk. Right. Okay, but you see, but there's something bothers us, right? This thing is very big. You say, I get a linear function of this one. This space nothing to do with rational points, arithmetic, but this thing has something to do with arithmetic. So the way to get rid of that one, we use the narrow-tensor Heidepperian EKAB, go to the real number. We have a narrow-tensor Heidepperian. Okay, so we use narrow-tensor Heidepperian. So that's a good place why we take 2 periods instead of 1 period. So this means that if I have 2 periods, PF 1 chi, I can take narrow-tensor Heidepperian PF2 chi inverse. I will tell you why I take chi inverse later on. I can take a narrow-tensor Heidepperian of this n. And usually when people do narrow-tensor Heidepperian, we use the Hermitian pairing. So the linear in the first one, anti-linear in the second one. But for our purpose, I will take a bilinear. So I didn't take conjugation. If we want a Hermitian pairing, then I have to write this one, the bar, take this away. But this is just bilinear. This is a bilinear. Bi-C-linear on EKB tensor C. So in the second one, I still take a linear, not an anti-linear. If I do this one, then this will be, if you think about it, F1, F2 goes to this part as a linear functional. So this one is inside C. You get C valued. So this defines a linear functional, a numerical linear functional in this space. So this gives a pairing on a linear functional an element. I give a name called a beta inside the home of pi tensor chi of C tensor home pi tensor chi inverse of C. Both them is invariant head cross. Right, I get a linear functional there. That's very interesting. So far, there's elliptic curve suddenly completely disappear. It just have 2 representation. You define a pairing there. Right? There's completely no arithmetic here. Right? This is a one-dimensional. This is irreducible representation of Zagier QH. Right? So there's nothing to do with the elliptic curve. Okay, this is the first observation. The first observation is that when you do this Peir's integral, take a narrow-tensor Heidepperian, you actually get a bilinear, bilinear functional. Okay, in this space. Well, unless we can do something with this space. I mean, the second one is is very interesting that this space is happen to be very small space. So the observation 2, I should not call it observation, it's really a bigger theorem, is by, the first one is completely trivial. I don't know what's the name of that. The second one, the Saito, Tano, and Vas-Puget. And Vas-Puget will be the second part. There are two parts. First part is this space actually has dimension at most 1. So it's a very tiny space. So this is at most dimension 1, this is at most dimension 1. Tensor product is at most dimension 1. So we so far define one element in the one dimension, at most one dimension space. So not only that, this one, of course, is the tensor product of the local one of pi p tensor chi p of C. So actually, each of them is at most dimension 1. And most of them is dimension 1. And so this one, this local space has dimension equals 1 if and only if. So this is something called epsilon factor of pi p chi p equals 1. So this is the epsilon factor of the Rankin error series I write at the beginning. Local root number. Okay, so the conclusion will be the following. Conclusion will be, so the consequence will be the following. Dimension home K cross pi tensor chi of C equals 1 if and only if. So this epsilon pi p chi p equals 1 for OP less than infinity. But you say I forgot about pi infinity. Usually your pi infinity, you take the trivial representation in this part. So this one, chi p, is always equal to -1. It's not a way to representation, it's a trivial representation. Now, I should not write this in, but it probably doesn't really matter here. So this is somehow we should, is a replacement, something called Hingen's condition. You remember, the Hingen's condition x naught of n, in some sense, implies this condition. But if you say, I want to consider all towers Shimura of a modular curve, you don't have something called Hingen's condition anymore, right? The Hingen's condition say every prime p divided n should be split in k, right? So that's the condition we use all the time. But in fact, this should be the replacement of the Hingen's condition if you consider all the towers. Okay, so this is the first part. Second part, even amazing, is that, well, you say this is one-dimensional, then can you give me a base of this one-dimensional space? So in automorphic form theory, usually it's very hard to get a base. Even you know the one-dimensional, it's very hard to get a precise base there. In the representation theory, when you start representation, you always combine the representation and its dual representation. In this way, you can create some numbers, right? Because dual, you get some numbers. The second part is interesting. So there is a base. So the space, so there is an explicit generator. Explicit generator. Let me call it alpha p is inside the tensor product of the two space. is called a matrix coefficient. And this generator, no matter, this is at most one-dimensional. If dimension 0, this generator is 0. Otherwise, this generator is always, in any case, is given by the following an obvious formula. Is given by alpha p of f1, f2. Oh, I completely forgot about that. So you see, okay, this is one more condition here. You're looking for this thing. This representation has trivial central character, right? I mean, for elliptic curve, the Galois representation, there's a trivial central character. So when this one restricted and Q head across, this one is non-vanishing if chi here is a so the one necessary condition. So I forget two conditions. This one and another condition that chi restricted on Q head cross equals 1. So this is something we call anti-cyclotomic characters, because that's necessary for this dimension. Because when you restrict the Q head cross, this one give you is a scale, is a trivial. Here, mapped to here, you must have this condition. So this formula is given by integration Kp cross Qp cross, and you have a control gradient. So remember, there's a pi. Tensor pi has a pairing. I will define the pairing later. I mean, we know there is a pairing by abstract nonsense, but actually you can define this one by purely geometrically. The pairing basically defined by such as that f is equal to degree of f. If f is from x gamma to e, but be really careful. You have to normalize this gamma because so it's defined by if this one is by gamma here, then this one you have to take the volume of gamma of x gamma. Right? So that when you change a different gamma, you will normalize this thing. So we have is a pi p of t of f1, f2, chi t dt. Right. Okay, I can check with that. Maybe you feel very strange. Why that thing is invariant this one, also invariant this one, right? That's because of conjugation property, right? Well, you see, if you alpha p, if I write one s inside k head cross, right? If I write s f1, f2, if we bring this inside, what do you get? You get this integration pi t of t and sf1, f2, whatever. Let me forget about this pi here, ts, right? Chi t dt. Then you change your variable, t goes to ts inverse, right? Then this one you will get chi ts inverse, right? Okay. So this one you get a chi of s inverse out. You can take it out here. Right, so this gives you chi s inverse alpha p f1, f2, right? So you move this to the other side, you get exactly this pairing, pi p times chi p here. Okay? Similarly, if you want to see other direction, you notice that you can rewrite this formula by this integration of let me forget this in TF1, F2, chi t dt. This will be, because the action is, the conjugate is the F1 T inverse F2 chi t dt, right? So this is something as integration of F1 TF2 chi inverse of t dt. So that's give you the invariant of other action. So you have two actions there. Okay, good. So we define this generate. It's not really, it's just the usual matrix coefficient. And then this matrix coefficient, you normalize a little bit. So normalize alpha p. You write this one as some Cp alpha p. Such that we're not going to write down them, such that the product makes sense. It defines the elements. I generate. Well, such that, basically such that alpha p f1, f2 equals 1 if fi are spherical base of these elements. So when you define that this tensor product, you need to choose some base, right? So you want to. Okay, so this will be a generator of these two spaces, the home of pi tensor chi of C tensor home pi tensor chi inverse of C. Okay, so I have two observations. The first observation is I defined a bilinear functional inner space. The second observation is this space is not very big. It's at most one-dimensional. Not only that, we know there is a base there. It's a generate, there. So the conclusion is that, if we combine both of them, you will see when this generalized Hingland condition, maybe I should call it Sato-Tenno condition in this case, you will, let's call this the Sato-Tenno condition. Sato condition is a sufficient and necessary condition for this space to be one-dimensional. So we combine the two observations, we will have the following picture. We combine two observations of 1 and 2. We give that, so if the Sato-Tenno condition hold, then there is a constant C inside complex number such that is beta equals C times alpha. Okay, maybe I took the product of alpha p would have a, right? Okay, so let's rewrite what does it mean. So if I write them up, so this is what we get. So equivalently, there exists a C inside complex number such that for any F1, F2 inside pi, then the Hingland points we defined we take a limited Hyperion, will be equal to C times this alpha normalized matrix coefficient of F1, F2. Okay? So that's the before you do any, this everything right at Blackboard completely formal. Before you do any calculation, you already end up with this conclusion. Right? So the Zagier formula, in some sense, is just trying to understand this complex, this constant C. Yeah, everything at Blackboard completely formal, nothing to do with arithmetic geometry. It's just automorphic form theory.
Can I ask you a question? You mentioned Volksberger before. Is there any Volksberger on the board so far?
Actually, I'm doing Volksberger. If we replace E by complex number, that's exactly Volksberger formula.
But you're not using his results in this formal.
These use a local result. These are local results. For example, this the second part is due to Volksberger. So this local function has a generate. Okay, so let me write down something if you want to remember. So in other words, maybe if you want one sentence, what the Zagier formula is about. So Zagier formula. So Zagier formula. So is a formula is about a decomposition, idyllic decomposition of a bilinear form. Pi tensor pi. Right, so that's the way we end up. Okay, now we want to write down what the exact formula is. So in this generality, let me rewrite the Volksberger theorem, which is some generalization. Okay. Maybe revisit as we did. So first of all, there's P f of chi as a function of f. You fix the chi, let f change. This is not identically 0 if and only if the derivative, if and only if I have two parts. The first part, there's a cytoteno condition satisfied. So the home pi tensor chi of C is not 0, or equivalently, this epsilon pi p chi p equals 1 for all p less than infinity. Right. So the first part is a local condition. The second part is the derivative of E chi 1 is not 0. Okay. So the both conditions satisfied, you get this Peirce integral is non-vanishing. When the Peirce integral is non-vanishing, then you have some whatever. Now you need to have a constant. The constant will be some whatever for any f1, f2 inside of pi. The Peirce integral I computed, pf1 chi pf2 chi, right? Now to the Hyperion. So remember, this is just the beta of f1, f2 equals, this constant is L prime of f chi 1, so times alpha f1, f2. So alpha f1, f2 is, you remember alpha, that's called sharp, right? Alpha sharp is normalized. You have real normalized back. So certain normalization may be stuck here. It's time constant. So this is the thing. Something like that.
Sorry, so alpha star is formally the product of the alpha p.
Right. So you normalize, then normalize back, real normalize. So in other words, the Zagier formula just said that the constant c there is nothing, just the derivative of error function.
But in the wall-per-day context, the constant is 1 if you use that normalization of alpha.
Yes. Or if you do that one, that would be more complicated. You have to divide by LF chi 1.
No, but yeah, but in the wall-per-day context with the sort of divergent normalization.
That's right. Yeah. So yeah.
Is there a way to normalize it here so the constant is 1?
No. Yes, because the local one exact same as the Raspberry one.
Yeah, right.
There's no change. Yeah. So what's actually said that actually you can, this constant can be easily remembered because when you define this matrix coefficient, when you normalize it, you get some number. Then you put this number back. Okay, as a few minutes, we're not going to continue. Just tell you this idea. You can just in GR2 case. Tomorrow I'll talk something more general case. Just in GR2 case, what else you can do? Yeah, some extensions. So one remark is, if we replace this Shimura curve, right? This one, I mean, this actually we write on the H upper plane of GR2 of AF by GR2 of Q. So that's essentially I write on there. If you write on, I mean, this thing's already of GR2 of usual ideals, right? Take this K infinity, right? Maybe take it R cross, whatever, of GR2. We'll put K infinity because we are only working on Shimura curve. You replace by usual GR2 of A of GR2 of Q, and E just by complex number C. Then you can redo the whole theory in a blackboard. Then, of course, in this case, the Peirce integral will be much simple. So you pick up any irreducible representation. So you'll have much a simple thing. You just think about all the functions. You have a pi, all the functions. The home, who knows what does it mean? Home of GR2 of Q, GR2 of A of C here, right? The home just means functions. Suppose this is a irreducible representation. I mean, you can then you can define that the P F chi is a complex number. Okay, just a complex number you get. Then you can define, so instead of considering narrow-tensor Hyperion, you can have F1 chi PF2 chi inverse. You can get something like that. In this case, you get exactly the same formula, except here you just have this pi chi 1 times this normalized the matrix coefficient integration. So this is the Zagier formula. So somehow the Zagier formula it's an elliptical version of a Puget formula. Okay, this is my first remark. The second one I want to say is that there's certain different variations, extensions of the sand. So we have the following extensions. The following, the other, there are other extensions. So I can write down there. So so the first thing is this works for Shimura curve. Why we need to work a Shimura curve? Remember, there is a condition here, right? So this condition forces you can only work on the modular curve. Say this condition is broken. I don't have this. This one is not a 1 all the time. So if LE chi S has odd function equation, then there exists a unique quaternion algebra B, right, and there such that, and also a corresponding Shimura curve such that, so this cytoternal condition is satisfied. Such that this home of pi Jacob-Lagrange correspondence tensor chi of C is not 0. Okay, so then you can have the Zagier formula. Then we have this P F chi not identical 0 if and only if the derivative F, the E chi 1 is not 0. Right, so this is the formula proved in a book, and the reference I said, the second book. Yeah. Xi Yiyuan, Wei Zhang, and myself. The second one, you have a periodic and Zagier formula. And the classical setting is done by Perrin-Rio and Kobayashi, whatever. And this generality is done probably in progress by Zagier. So here you just replace Néron-Tedder-Hyde pairing by periodic Néron-Tedder-Hyde pairing. So the error function will be some periodic error function. So the last one I like to call the periodic Puget formula. Or BDP formula. So here, the Néron-Tedder-Hyde pairing. So this is a complex number. It's replaced by log, the formal log of P F chi times F1 log F2 chi inverse. Okay, so let me write down. These have X of CP mapped to E of CP by F, right? Here you take a formal log to CP, but pick some differential form. Okay, so this will be a bilinear form, the value in CP. Right. So you can also get a formula like that. This is It's done initiated by Ottolini, Damon, Prasanna. And this generality is done by Liu and Wei Zhang. And I have something there. So, but if you think about this thing, it's very interesting. You have 4 formulas. There are two Zagier formula, 2 Zagier formula. So it's really, you have 2 coordinates, the p-adic word, complex word. The one called second coordinate is you want a special value or derivative. So all the combination of the 4 formulas. And the Gross asked me, do they have idyllic formula to combine everything? That's I don't know. Maybe some motivic version of this kind of thing like that. Okay, maybe I should stop here.